Hello, welcome to Trigonometry section 6.1. In this section, or in this video, we're going to go through and talk about angles, arc length, and circular motion. This is going to be a quick, brief overview of the section, as quick as I can make it. If you have any more questions, you can leave them in the comment section below, or if you're my student, you can text me. All right, so here we go. Let's get started first with angles. You need to know that there are both positive and negative angles. Both of these start at 0 degrees on the right, and positive angles go counterclockwise. So if I start at 0 and spin back to this axis here, I've gone 90 degrees. That is positive 90. Positive angles go counterclockwise. If I go another 90, 90 and 90 is 180. Another 90 is 270. And then I come full circle. A full circle is 360. Now, if you want, you can keep going and you can do another 90. So equivalent to 90 would be 450. And then 180 would be 540. And you can keep going around as much as you want. If you want smaller angles, you can figure those out. For example, if we cut this in half here, what is half of 90? 45. So we can figure out that angle. And then if we go 45 and 45 is 90, then we could go another 45. 90 plus 45 is 135. And then if we go another 45, we get to 180. So you can figure out other angles by doing some simple math. We also know that 90 is divisible by 3. And so if I use a different color here, we could count by 30s. Okay, so 30 and 30 is 60. And another 30 is 90. So you can do by 30 degrees also and get your positive angles. Now, looking at the other coordinate system, guess what happens if you spin clockwise? You get negative angles. So this would be negative 90, negative 180, negative 270, and if I go full circle, that's negative 360. And you can do the same thing with your negative angles. Half of 90 is 45, so there's negative 45. And then if I want to count by 30s, I can say negative 30, another 30 would be negative 60, and then getting us to negative 90. And then you can keep spinning around clockwise, getting your negative angles. Okay, so the most important point there is positive angles go clockwise and positive angles go counterclockwise and negative angles go clockwise. Next, you're going to need to know how to convert from degrees, minutes, and seconds to decimal degrees. Probably the calculator is the easiest way to do that, but to show how to do that manually, if you've got degrees, minutes, and seconds, and you want to convert to decimal degrees, you're going to start with your seconds, and you're going to divide that by 60. And if I pull up the calculator, 21 divided by 60 is, as a decimal, 0.35. And then what you're going to do is you're going to take that decimal value and you're going to attach it to your minutes. So then that's going to give us 60 degrees, 42.35 minutes. Do you see how that worked? So the 21 divides by 60 gives us 0.35, and that then gets attached to the minutes, okay? And then the next step, now is to take your minutes and divide by 60. So you like do division by 60 repeatedly. And so if we bring up the calculator, now we need to do 42.35 divided by 60. And as a decimal, that is, and they're probably going to want you to round to so many decimal places, okay? So we could say that this final answer is 60 degrees. Let's see, what was that again? Come on. 0.70583 repeating. 70583 repeating. If you wanted to write it exactly, it would look like that. If you wanted to approximate it, it might be 60.71 or 706 or and I just realized that I wrote the degree symbol in the wrong place there. Degrees. There you go. So either of those could be acceptable depending on where they want you to round, if they want you to round. And you'll have to know how to round to a certain place of decimals correctly, okay? So there's going from degrees, minutes, and seconds to decimal degrees. You're also going to need to know how to go the other direction. And if you notice, we divided by 60 to get to the decimal degrees. So to go the other direction, we're going to multiply by 60. Okay, so we're going to take the decimal portion of the degrees and multiply by 60. And then the whole number part here, the 40, becomes the degrees. And we're going to bring up our calculator and do 0.32 times 60 as a decimal, 19.2. And that'll give us 19.2 minutes, okay? Now to get the seconds, you again take the decimal portion and multiply by 60, okay? So then that's going to give us 40 degrees. Again, the whole number here, the 19 is the minutes, and then whatever we get from the multiplication will be the seconds. Okay, so that's going to be 0.2 times 60, which is 12 seconds. And so there's going from decimal degrees to degrees, minutes, and seconds. And now we've covered that both directions. So now let's look at converting between radians and degrees. Okay, so what you need to know is to go from degrees to radians, you multiply by pi over 180. And to go from radians to degrees, you multiply by the reciprocal. 180 over pi. Now, if you're wondering, how do I know if it's a degree or not? How do I know if it's a degree or a radian? Well, it's from the degree symbol. If there's a degree symbol, then it's a degree. If there's no degree symbol, then it's a radian. That's how you know that it has nothing to do with pi. It has to do with whether or not there's a degree symbol. Okay? So let's see if we can finish this out then. If I do this first degree, the 330 degrees, and convert to radians, what I'm going to do is I'm going to multiply straight across. But if you notice, this is understood to be over 1. I can simplify before I multiply. So I can divide these both by 10. And then does anything go into 33 and 18? Yeah, 3 does. So 3 goes into 33 11 times. 3 goes into 18 6 times. And then if I multiply straight across, I'm going to get 11 pi over 6. That is converting degrees to radians. Now, if I want to, I can also use my calculator. So if I bring up my calculator, just to show you, we can do 330 times, and then as a fraction, pi over 180. And notice the calculator verifies it's 11 pi over 6 or 11/6 pi. Either way is fine, okay? Now, on the other one here, going from radians to degrees, notice that my pi's cancel, and then I'm going to simplify before I multiply. 15 will go into 180 how many times? 15 goes into 18 once with a remainder of 3. 15 goes into 30 twice. So that's 12 times. And so this is a 1 and this is a 1. And then if I multiply straight across, it's going to be something over 1, which is just going to be a whole number degree. And we can figure that out doing 17 times 12. 204, and it's going to be negative because the original angle was negative. So that's going to be negative 204 degrees. Negative 204 degrees. And just to show you again the power of the calculator, we can actually do this all on the calculator. Negative 17 over 15 pi. If you want to put the pi to the side, you can. If you want to put it in the top, you can. Either way is fine. Times the fraction 180 over pi. And notice the calculator does it all for you. So you can do it manually or electronically. But the main thing you need to know is that going from degrees to radians, you multiply by pi over 180. And to go from radians to degrees, multiply by 180 over pi. And now let's do it showing you how to get a decimal answer if you need a decimal. So multiplying negative 40 degrees by pi over 180. And we're going to assume that they say approximate this to the nearest hundredth. Let's say 2 decimal places. And so we're going to take our handy dandy calculator and we're going to say negative 40 times pi over 180. And notice that my calculator is going to give us the exact answer in terms of pi, but if they want a decimal, you can hit this SD button and it makes it a decimal. Now we need to round that to 2 places, tenths, hundredths. Behind the 9 is an 8, and so that 69 is going to round up to a 70. So that's going to be negative 0.70 to the nearest hundredth, okay? Now, here we have another radian. Again, we know this is a radian because there's no degree symbol. We want to convert to degrees, so we're going to multiply by 180 over pi. And let's say they want this approximated to the nearest hundredth, okay? So again, we're going to pull up our handy dandy calculator. 9.28 times 180 over pi. And rounded to the nearest hundredth, I see a 4, which makes that stay 70. 531.70. And don't forget your degree symbol. If you don't put the degree symbol, that means it's a radian, so that's a degree. And there's 2 examples going both directions, radians to degrees and degrees to radians, okay? Next, arc length. We have a formula for arc length, S equals R times theta, and you need to know that theta must be in radians. So in order to plug into this formula, if you're given an angle in degrees like we are, you're going to have to convert it to radians. Or If they give you S and R and they want you to solve for theta, your answer is going to come out a radian. And then if you need a degree, you'll have to convert it back to degrees, okay? So theta must be in radians to plug into this formula. Theta is going to come out as a radian if you solve for theta. All right, so let's get rid of that stuff. And let's see how to work this example we have here, okay? We are given a radius of 3 meters and a central angle, the angle subtended by the central angle, 120 degrees. And the first thing we're going to have to do is convert degrees to radians. And we just covered how to do that. So we're going to multiply by pi over 180. And I'm going to simplify manually, dividing by 10. What goes into 12 and 18? 6 does. 6 times 2 is 12. 6 times 3 is 18. And so that's going to give me my theta as a radian. And then I can solve for the arc length, which is S. S is the arc length. That's going to be R times theta. And we're going to approximate that, let's say, to the nearest hundredth again, okay? All right, so we've got 3 times 2 pi over 3, which is exactly 2 pi, which is 6.28 rounded, okay? Bam. And I probably, if you notice, I could have done that manually because 3's cancel. Leaves me 2 pi, which is about 6.28. And the units for arc length are going to be the same as your units for the radius, which is going to be meters. And just to give you an idea of what we just calculated, okay, let's say that we have a circle which has a radius of 3. And if we have an angle of 120 degrees, what we just calculated is the distance around this arc here, this distance right here. Got it? So 6.28 meters is the distance you'd have to walk around this circle if the circle had a radius of 3 meters and you walked around an angle of 120 degrees. That's what you found. That's what the 6.28 represents. And so the most common application I can think of for this formula is pizza. Let's say that you order a stuffed crust pizza and you know the angle of your slice and you know the radius of your slice. You can calculate how much cheese is in your crust. If you were to take it out and lay it out in a straight line, that would tell you the length of your cheese in your stuffed crust, okay? Anyway, that's just an application there for that. Next, area of a sector of a circle. We have this formula. Again, we got to note that theta must be in radians. So again, in order to plug into this formula, your angle has to be in radians, or if you're given the area and the radius and you want to solve for theta, you're going to get a radian angle out of it. Got that? Radians goes in, radians comes out. If you need degrees, you'll have to convert it. So again, we have another another example here. We're given a radius of 9 feet and a central angle of 50 degrees. We want to find the area of this sector. And so the first thing we're going to have to do, since we're given a degree, is convert it to radians. So we have pi over 180. That's our converter. Divide by 10. That's going to give me 5 pi over 18 radians. And then I can find the area by plugging into the formula. 1/2 r squared times theta. And again, what a nice time to bring up the calculator. Here we go. 1/2 times 9 squared times 5 pi over 18. Now, some of you may be watching this and thinking, do I have to input it like that with the parentheses, or can I just do a time symbol, times and a times, and that would be fine. You don't have to use the parentheses. You can, or you can just put a multiplication symbol in there. Either way is going to work. And then if I hit equals, it's going to give me the exact answer in terms of pi. I'm going to have to hit the SD if I want a decimal. 35.34. 35.34. Now remember, this is an area, so if our radius is measured in feet, this is going to be square feet. Area is always square units, and that's going to be how many square feet. Now again, if I was to draw a picture of what this represents, let's say we have a circle of radius 9 and an angle of 50 degrees. Okay, what we just calculated is the area of this sector, okay? And since I like talking about pizza, the application for this could be pizza. Let's say that you have a slice of pizza, you know the radius of that slice, and you know the central angle. You can use this formula to calculate how much cheese is on that slice of pizza. Or if you were going to cover it with marinara, how much marinara it was going to take to cover that, okay? So that's the area of the sector of the circle. And finally, we're going to talk about linear and angular speed. We have a formula here that translates linear to angular speed. And I guess the first thing to note is that the linear speed is the v, and the angular speed is, well, it looks like a W, but it's omega. That's the lowercase Greek letter omega for angular speed. And of course, r is your radius, okay? So again, if we want to look at an example of what we're talking about here, let's say that we're spinning something that's tied to a string, like a yo-yo, okay? Let's say that we are holding the end of the string, and over here's the yo-yo, and we're spinning it around in a circle, okay? It's going to make so many revolutions per minute, okay? So we could say the angular speed is so many revolutions per minute or per second, per hour. It doesn't matter really what the time is. You can use any time unit you want, but it can be a number of revolutions per time unit, okay? And that's how fast it goes in the circle. You're going to have a radius, okay? And as you swing this thing around in the circle, what happens if the yo-yo breaks and comes unattached from the string? Is it going to continue to go in a circle? No, it's going to shoot off in a direction like this, and then that becomes linear speed, okay? So as long as it's going in a circle, it's angular speed. If it comes unattached from the string, it's going to go in a, well, approximately straight line. If there was no gravity, it would go in a straight line, but it's going to take off in some linear speed, and then that's going to be like meters per second or feet per minute or whatever, okay? It's going to be so many feet per minute or miles per hour. It's going to be some length over time unit. And so what we're going to do is we're going to look at an example here. We've got, let's just say a tire. This might be a tire on your vehicle, okay? It's a 15-inch radius tire, and it's going at 30 revolutions per second. And we want to calculate how many miles per hour you're going if this is the information from your tire. That sounds like a good problem. All right, so let's see here. First of all, we've got our angular speed measured in 30 revolutions per second. This tire is making 30 rotations every second. In order to calculate with an angular speed, it has to be converted to radians per second, okay? So we're going to have to convert revolutions per second into radians per second. So here's my question. When this tire makes one revolution, how many radians has it gone? One revolution is how many radians? Well, we know one revolution is 360 degrees. And so I guess you need to know that 360 degrees in radians is 2 pi. Okay? So one revolution is equivalent to 2 pi radians. The reason I put the revolutions in the denominator is because over here revolutions were in the numerator, and I want those to cancel. So now when I multiply straight across, I'm going to get 30 times 2, which is 60 pi, and now I'm in radians per second. Okay, so now I've got my angular speed in radians per second. Now I can plug that into my formula. Okay, so with my radius and my angular speed, I can now calculate linear speed. So that's going to be 15 inches times 60 pi radians per second. Okay, and I guess another thing you need to know is that radians is really unitless. So the radians is going to disappear, and we're going to end up with inches per second when we multiply, okay? So we need to do 15 times 60 pi, which is really just 15 times 60, which is 900 pi. And now that is inches per second, okay? 900 pi inches per second, which if we're talking about how fast is the car going, inches per second, I don't really understand that. What I really understand is miles per hour. So now we're going to convert the 900 pi inches per second, we're going to convert that into miles per hour. And so the first unit fraction that I'm going to use to do that is I'm going to do a unit fraction to convert seconds to minutes, okay? So seconds are on bottom. I want to get rid of the seconds. So I'm going to put seconds on top. We know that 60 seconds is 1 minute. That'll get rid of my seconds, but it'll get me minutes. What I really want is hours. So I'm going to use another unit fraction to get rid of my minutes and get hours, okay? So I also know that 60 minutes is in 1 hour. That'll get minutes to cancel. That'll leave me with hours, okay? So at this point, I've gotten rid of my seconds, and I'm now into hours. And let's switch color, because the next thing I'm going to do is get rid of my inches, and instead I want miles. Okay, so inches are on top. I want to get rid of inches, so we're going to put inches on bottom. And I happen to know that 1 foot is equal to 12 inches. Here the inches are going to cancel. But then I've got feet, I need miles. Okay, so I happen to know that 5,280 feet are in 1 mile. So there's another unit fraction. And the reason I'm calling it a unit fraction is because these two units are equivalent. 1 mile is equal to 5,280 feet. The feet are going to cancel. That's going to get me in miles. And so then I'm going to have miles per hour. Okay, so now what do I do with this? Now I'm going to take this 900 pi, multiply by 60, multiply by 60. That's going to give me my numerator. And then in the denominator, I'm going to take my 1 times 1 times 12 times 5,280, and that'll give my denominator. Okay, so let's pull up our calculator. And let's bring this over here where we can see. What did I say? I said we want to do 900 pi times 60 times 60. Wow, that's a big number, okay? So that's going to be our numerator. Is there any way to keep this on top? Nope. Let's see. Okay, forgive me for a second. I'm going to move this up here out of the way so I can still see it. You can't, but I can see it. 10178760.2. And that's rounded, okay? That's my numerator, and the numerator is miles. And then in the denominator, now we're going to bring this back down here. Okay, clear. In the denominator, we're going to do 1 times 1 times 12 times 5,280, which is really just 12 times 5,280, and that's my denominator, 63,360. And that is hours in the denominator, okay? And so then we're going to divide that out, and we're going to get our speed in miles per hour approximately, okay? So I'm going to actually go back here to grab that number, and I'm going to hit that number divided by 63360. Oh, that can't be right. How did I get 1? Clear. Okay, let's do this. Okay, this equals, now I've got that stored, divided by 63360. Okay, that sounds better. And did you see me make a mistake? And I used my common sense to say that doesn't feel right. And I went back without just mindless button pushing and taking whatever the calculator gives me. What is that? That is 160.6. If we round to the nearest mile per hour, that's 161 miles per hour. Okay? So just to reemphasize what we calculated, if your wheels, if your tires on your car have a radius of 15 inches and they're rotating at 30 revolutions per second, you are traveling 161 miles per hour. And that's how you actually do those linear speed and angular speed problems. And that's going to do it for this lesson, section 6.1. If you have any questions or comments, you need me to work other examples or you need further explanation, you can either leave a comment in the comment section below or you can text me. And thanks for watching.